In this video, I'll show you how to implement a linear system in R. The standard linear system equation, as we know, is Ax equal to B, where A is a matrix of the coefficients of the linear equation. X is a vector and B is a vector, so column vectors. So we are not dealing with a scenario of a homogeneous system where Ax is equal to 0. So this is not in the scope of this video. So let us see how a linear system can be defined. As we all know, Ax equal to B. That implies X equal to A inverse of A into B, right? This is all you know from your knowledge of matrices. And the way X is defined is it is equal to X equal to 1 by determinant of A adjoint of A into B. So I hope you know this formula. So the idea is not to go to the theoretical part, and assumption is you are aware of these basic things. So X is equal to 1 by determinant of A adjoint of A into B. This is primarily because A inverse is equal to adjoint of A divided by determinant of A, right? So considering this, we can further derive that determinant of A into X is equal to adjoint of A into B. So this is what is primarily we will be using this formula. And if you see in this example, in this equation, we just cross multiply it, you get this final outcome. Now let me write this final outcome once again so that you can remember. So basically we have a determinant of A into X is equal to adjoint of A into B. Is a matrix multiplication. Now, having said this, now we can translate the various types of linear system, whether they are consistent systems or inconsistent systems. So this is the formula that we will be using, and later on we will move to Cramer's rule in our subsequent discussion. Now, the classic definition, we're not talking of Cramer's rule right now, the classic definition of finding out whether a system is consistent or not. So a consistent system will either have a unique solution or it will have infinite solutions. A non-consistent system will have no solution. That's the basic we know, right? Now let us say how do we crack this problem using this formula. So what we have to find, if you see this equation, we have to find the determinant of A first. Now if I plot it in a flow chart, so determinant of A, you got to find first the determinant of A. Now if the determinant of the A matrix if the determinant is not equal to 0, then we can say that we have a unique solution. The linear system has a unique solution. Otherwise, if the determinant is if the determinant is 0, if the determinant is equal to 0, then we can have two scenarios. One, if the adjoint of A into B is not equal to 0, then system has no solution. Then there is no solution, and we say this is inconsistent. However, if the determinant is of A is 0, but the adjoint of A into B is 0, then the system has infinite solutions. So this is the backbone of implementation of a linear system before we go to the Cramer's rule. So if you see the formula here, the determinant of A into X is equal to adjoint of A into B. So it means if the determinant is, you first have to find the determinant of A, and if it is equal to 0, that implies if your denominator is equal to 0, and your numerator as well, and numerator is not equal to 0, so it has no solution mathematically. And here it implies if both the numerator and the denominators are 0, then there could be infinite solutions. So I mean, roughly we can say that, not in the exact sense. So based on this, we are going to implement the solution in R. Now let us take one example of a linear system, a very basic example, and we'll see how we can implement in R. So we have 3x plus 6y minus 4z equal to 3. Equation number 1. Equation 2 is 3x minus z equal to 0. Equation 3 is 12x minus 6y minus z equal to minus 3. So we have 3 variables and 3 equations. So basically we are dealing with a square matrix here for A. So we can write A as 3, 6, minus 4 in the form of matrix, the coefficients. So as you know, 3, 0, minus 1, 12, minus 6, minus 1. So this is pretty simple. And here we say x, y, and z is equal to the value on the right hand side. Okay, it's not quite right. Let me erase it. Okay. 3, 0, minus 3. This is all we have with us, and now we have to implement this linear system using this flowchart and the formula. So how do we do it in R? So if you see, we need to have 3 matrices defined. This is the coefficient matrix, the variable matrix, and this is the matrix on the right hand side. So we got to define the matrices and solve it. Now I will use the traditional method using this flowchart, and then we will jump to the Kramer's rule, and I will show you how to implement it using Kramer's rule as well. So let us go to the RStudio and see how it works in R. Now, if you remember, the first thing I will show you is how to create a matrix in R. So there are many methods, and let me see how to create a matrix. Now, there are many methods, and depending on your comfort, you can choose either one. I'll show you some of the methods that I'm aware of. Method 1, and this is the method which I normally do use. This is 3, 6, minus 4, 3, 0, minus 1, 12, minus 6, minus 1. So let us go and validate this once again. 3, 6, minus 4, 3, 0, minus 1, 12, minus 6, 1. 3, 6, minus 4, 3, 0, minus 1, 12, minus 6, minus 1. Okay. So now if you see the order of these coefficients is actually by row in the equations, right? The first row, second row, and the third row. So 3, 6 minus 4 is 3x plus 6y minus 4z, then 3x minus z, and 12x minus 6y minus z, right? So we need to define a matrix. So we need to define a matrix where we say that we use this data from A. We will say the n row equal to 3 because it's 3 by 3 matrix, and call, so n call equal to 3 by row. The reason is the data is arranged by row, as I showed you. So is this true? And we execute both the lines. So if you execute both the line, I did a mistake. Sorry, this typo error. And go to column. Let us run it. Yes, and we have a matrix A. You can display it. So 3, 6 minus 4, 3, 0 minus 1, 12 minus 6 minus 1. There is another method to do this same task in a different way. So before I do the second method, show you the second method, I'll clear the first matrix. So second method is again it's a simple method. So depending on what you prefer, this is something you can do straight away. You don't need to type more number of lines. 3, 12, 6, 0, minus 6. Minus 4, minus 1, minus 1. So 3, 3, 12, 6, 0, minus 6, minus 4, minus 1, minus 1. So basically, if you see this, we are using column wise instead of row wise. In the first case, we have, in this case, we have taken it row wise. Here, we are taking it column wise. So 3, 3, 12, 6, 0, minus 6, minus 4, minus 1, minus 1. And we say then for dimension, which is equal to 3 by 3 matrix. And straight away you can create the matrix. So I think again I have done some typo error here. You're seeing 3, 3, 12, 6, 6, 0. Okay. Okay. And you can see the same matrix we get 3, 3, 12, 6, 0, minus 6, minus 4, minus 1. And 1 and minus 1. So fine. There is another method you can use if you are still not happy with these methods. You can use tedious method of a row bind. Okay, so let me clear this matrix before I show you the third method. So you can create vectors of the coefficients of each of the variables 3, 3, 12 for variable x. You can create a vector for variable coefficients for variable y, 6, 0, minus 6. And similarly, you can create the vector for the coefficients of the variable z. So, and then you can use the column bind, because you are using the coefficients of the variables which are arranged column wise, right? So you can take A1, A2, A3 and bind this, and you can execute this. Let me show you. Let's execute this. So this is executed and you get a value of, you get a value of A. This is the same thing. So, I mean, you can still have another method where you, instead of using column bind, you can as well use row bind. So, I'm not going to show that. It is again very simple, and you can try your own. So basically, there are various methods where you can, by which you can create the matrix. I'm removing the last one as well, and I will use the method that I like. So I will use the first method. I mean, it depends on individual's convenience. Okay, so now we are done with the matrix A. What is it that we need to have here? So for matrix B, it's pretty simple. I will use the same method which I used for matrix A for matrix B. So I'll copy this and I will use the same method for matrix B. If you remember, matrix B is the right hand side of these three equations which I showed you. So I will use this method. Okay, so I don't need a data, so we can directly pass the vector here. So it's 3, 0, and minus 3. And call is equal to 3. Now the number of rows is 1, by the way is true. I'll show you if you are confused. Let me show you this. So here you can see 3, 0, minus 3. So this is exactly what I'm doing. Okay. So this is the matrix B with a vector 3, 0, minus 3 and row 3 and column is 1. It's basically it's a vector with 1 column and 3 rows. And if you run this, you get this matrix, right? One important thing to understand here is I'll be using the libraries from MATLib. So I don't know whether you pronounce it as MATLib or MATLib. So basically I'll be using this. If you don't have installed in your RStudio, you go ahead and please install it. Without MATLib also we can do this, but there are certain functions which I will show you which you will not be able to run without using MATLib. So I will prefer this. So I will add this library MATLib. I've already installed it. So if you have not done, then you have to run the installer packages and you can install MATLib or MATLib and then can proceed. Now we have now matrix A. We have matrix B. So let me show this and enlarge this. So you have a matrix A and matrix B, right? And the fact which I was telling you about MATLib is I can show you one display here, beautiful example how you can use MATLib here. If you want to see the equations, right? Equations. What is the linear equation that we are solving here? So show equation AB. So I'm sorry, I made a mistake here. I did not run the MATLib. Okay. So basically, this shows, if you see the result here, so this shows the equation that we are trying to implement in R. Okay. So this is the beauty of MATLib. If you see this, let me once again write this. I'm sorry. Let me once again write this. So equation. If you see here, it pops up a function from MATLib, right? So this is not there in RStudio by default. So you have to install MATLib and you have to include the library. Okay. So now, anyway, we'll go back to the classic example of how to solve it. But before that, let us find out the determinant of A here. It's a simple function. You can write determinant of A and run it. So determinant of A is 0. So the matrix A has a determinant which is 0. Now if you go back to the model which we were discussing, so if a determinant of A is 0, let me go back to that. Okay. If the determinant of A is 0, then either it has no solution or infinite number of solutions. No solution if the adjoint of A into B is not equal to 0, or infinite solution if the adjoint of A into B is equal to 0, right? So basically we need to find adjoint of A and adjoint and multiply it with B and find the final result. So this 0 is basically is a null matrix. I'll show you how it works. So just go back to our R. Okay. Now let us say we have to calculate the adjoint of A. So what I will do is I will create a variable adjoint A and I will run a function adjoint. So again this adjoint function comes in MATLib. So this is handy. So this is what I was telling you. And adjoint of A. So if you run this, this is the adjoint of A. Okay. This is the adjoint of A that we are getting. We're not using the pen and paper to calculate the adjoint using coefficients and cofactors and all. This is the R implementation. And the way we multiply its point of view, the way we multiply in matrix is using this symbol, percent multiplication percent, and we will see its point of A into B. So we run it and we get a null matrix. That means its joint of A into B is a null matrix, it's 0, and hence it has infinite number of solutions, right? So we can say here that it has infinite solutions. Now, to find the solutions, you have to take a pen and paper and substitute the value of x, y, or z as a k or whatever real number, and then you can find it out with relative to that, right? So this is something not a difficult part, but anyway, let me show you. The idea is not to teach mathematics here, but still the way you can, once you know that the adjoint of that determinant of A is equal to 0 and adjoint of A into B is a null matrix or 0. So the way you can find it out is we have an equation. Out of the three equations, one equation is 3x minus z equal to 0. Let me show you that equation here. 3x minus z is equal to 0. So what you can do is you can substitute any real number for z. Let us say z is equal to k, and you get a value, corresponding value of k in terms of z, right? So you get x in terms of k. So x equal to z by 3 to k by 3, and subsequently you can plot the other value. So that's not the idea of this tutorial. So we'll be focusing on R. Fine. So that's the way you can solve it. Now there is another method which is very, very simple method. You don't have to find a joint and multiply it to find in R. There's a method, there's a function called solve, and I'll come back to this function when we discuss Cramer's rule. So straight away you can find out. So it will tell you that error in solve or default system is exactly singular. So this has meaning, so you can just find out. So this says that this has infinite solution, there's no unique solution. Had there been a unique solution, this would have worked, but anyway, I'll come back to this function later on. So this is the way you can implement it in R, right? So now we'll talk of Cramer's rule in a little bit, and then probably we will try to solve the same problem using Cramer's rule as well. So let us park it for the time being, and we will discuss about Cramer's rule. Okay. So what is Cramer's rule? So this is, as you know, this is not the perfect way of writing, so I'm sorry for this. So Cramer's rule. So if you have equations like a11x plus a12y plus a13z equal to b1, then a21x plus a22y plus a23z equal to b2, and a31x plus a32y plus a33z equal to b3. Then basically your determinant is the determinant of say delta is a11, a1, sorry, a12. I'm sorry, let me fix it. Okay, a12, a13, and so on. This is a21, a22, a23. It's nothing but arranging the coefficients in order in a matrix format and finding the determinant a31, a32, a33. This is delta, and what we do here is we find delta 1, delta 2 and delta 3 if we have 3 variables. So, and substitute the value in the right hand side of the equation, b1, b2 and b3. This is the right hand side of the equation, right? b1, b2, b3. We substitute this column in the first column for delta 1, second column for delta 2, third column for delta 3. So basically we write it in this format: delta 1 equal to, these are the theoretical parts, so I am assuming that you are aware of it. The idea is to implement it in R. So delta 1 will be, we'll start with b1, b2, b3. Basically for the coefficients of the first variable we are replacing the values in the right hand side, and here it will be a12 as usual, a22 and sorry, let me make it a little bit clear, and a32, this is a13, a23, a33. So this is delta 1, and similarly you have a delta 2 where you have this in the format of a11, a22, a32, but you will replace b1, b2, b3 here. So b1, b2, b3, and the third column will remain the same. That's a13, a23, a33. So basically what we are doing in delta 1, we are replacing this column with b1, b2, b3. In delta 2, we are replacing this column with b1, b2, b3. And similarly, in delta 3, delta is basically determinant, right? So we are replacing the third column of the coefficient matrix. So coefficients of the linear equations, and here we are replacing b1, b2, b3. So this is what we have to find out. Okay, there is a slight typo. Let me correct it. a11, this should be a21, and this is a31. So this is anyway understood. These 3 values as per Cramer's rule, and Cramer's rule says that if delta is not equal to 0, in our previous example it was 0, then it has a unique solution. If it is not equal to 0, it has a unique solution, and solution is the first variable is equal to delta 1 by delta, second is delta 2 by delta, and third is delta 3 by delta in a 3 by 3 matrix system. So basically it says the first variable is equal to determinant of 1 divided by determinant of the main matrix or the coefficient matrix, and so on. So we have taken 3 variables as an example here. Now the Kramer rule also says that if delta is equal to 0, then we have a similar flow chart. If delta is equal to 0, then we have a flow chart where it says 2 things. Okay, the first is, okay, I'm sorry. Okay, the first case is if delta is equal to 0, but at least one of delta 1, delta 2 or delta 3 is not equal to 0, then there is no solution. Then this linear system has no solution. This is what the first part says. The second part says if delta 1 is 0 in any case, and delta is 0 and delta 1, delta 2 and delta 3 all are zeros, then this system has infinite solutions. Okay, so basically it says out of any of these determinants, determinant 1, determinant 2 and determinant 3, if one turns out to be not a null matrix, then it doesn't have a solution. And if all these determinants are null matrices, then it has infinite number of solutions. So the example that we took should fall into this category, right? Let us go back to the studio and see how we implement this using Kramer's rule. Okay, so we know the determinant of A. We have already found out that it is 0. The task is to find out determinant of A1, A2 and A3. Now, how do we substitute when we say A? If you remember, this is the value of A. This is the value of A. And this is the value, sorry. This is the value of B. Now, if I have to substitute this column in this column, what is it that I have to do? It's a simple method. So the way I do it is, I will take A1 as a copy of A so that I don't mess up with A, and then I will say A1 sorry, this, right? So this equal to, I will put it as B. So basically, if you see this, I'm substituting the first column of A1 with B, and then I print A1. So this is what should happen. Sorry, I did a mistake, typo. Right. Okay, I did not run it. So I've substituted the first column of A1 with B. Now I have, similarly, I'll do it for A2 as and A3 as well. I'll just copy paste it. I'll keep it as A2. So for A2, remember, we have to substitute the second column, not the first column. So this should be second and this should be third. Okay, so this is what you have to be very careful here. Now if you run A2 and A3 as well, so you have now A2 as well as A3. Now as per Kramer's rule, we have to find the determinant of a1, a2, and a3. So determinant of a1 is 0, determinant of a2 is 0, and determinant of a3 should also be 0, because we have earlier found out that is the infinite, this system has infinite solutions, so this is 0. So now we arrive at the same situation using this method, using the adjoint method. And here also we found that is infinite solution. Here also we found the same thing, but this is quite simple and very shortcut. So I prefer Kramer's implementation in R. So in similar kind of problems, where it is very simple, and even you don't use MATLAB here, but then fine. It's up to you. I like MATLAB, so I use the particulars in the libraries. So this is how we implement it. Let me clear everything now. We will be using these again, so it's better to clear. So this is how we implement it, right? Now there is a similar. I'll take another example which will have a unique solution. And here, because in the previous case we had infinite solutions and we had to substitute it with some real number, and we had to find, and that can be infinite number of solutions depending on the real numbers. That's fine. But let's take an example which is a little bit challenging. I'll show you why it is challenging in terms of unique solution. So this is our next example, and the next example that I will show you, we will use another equation. Let us go back to this module. Okay, so I'll write it fresh here. So we have another system, x plus 2y minus z equal to 1, 2x minus 2y plus 4z equal to minus 2, and minus x plus 0.5y minus z equal to 0. So basically what we are saying is here the matrix A is equal to 3, 2, minus 1, 2, minus 2, 4, minus 1, 0.5, minus 1, and matrix B is equal to the value, the right hand side, the value on the right hand side, 1, minus 2, 0. So this is basically our equation, right? 3, 2, minus 1, 2, minus 2, 4, minus 1.5, minus 1. Let us implement it in R. We have seen it already, how we define a matrix, so we'll quickly write the matrix and we'll implement it. So I will use my favorite method of defining a matrix. If you remember, 3, 2, minus 1, 2, minus 2, 4, minus 1, 0.5, minus 1. We'll validate later on once we create the matrix whether we have taken the right numbers or not. So n row equal to 3, same stuff again, and it's again 3 by 3 for simplicity, all equal to 3, and by row equal to 2. So run it and see whether I've done a mistake here. 3, 2, minus 1, 2, minus 2, 4, minus 1.5, minus 1, and row 3. Okay, again I messed up with this. This is a comma. We have some mistake now. This is the comma, this is an extra mistake. Sorry for this. Okay, so 3, 2, minus 1, 2, minus 2, 4, minus 1, 0, 5. It should be correct. 3, 2, minus 1, 2, minus 2, 4, minus 1.5, minus 1. Okay, this is fine. Let us create the matrix B now. Uh, 1, minus 2, and 0. And row equal to, be careful here, we have one column. This is a vector with one column. We are writing it in a matrix format, so be very careful. Okay. And we can display B as well. So this is 1, minus 2, 0, fine, we have done it. Now, we will first use the famous method here, and then we will go to the classic method. Okay, so this is very simple. If x is equal to b, and if determinant, we have said in famous method, the determinant of a is not equal to 0. So here it is minus 3. So you can see here determinant of a is minus 3. Now if you want to see the value here, display the value here, so you know it, right? So you can say b is a variable and put the variable in the determinant and print the variable. That way also you can do if you want. So b is here is minus 3. So basically it is not a 0. So that implies that this has a unique solution. And if it has a unique solution, we don't need to get into all the mess of calculation. If we are using R, we can straight away find using solve function. So we know that x is inverse of, as we said, if ax is equal to, if ax equal to b, we started with this, then x equal to inverse of a into p. So that is what we can write here. So we can say that when x is equal to inverse is a function actually. That is again, if you see, is a matrix function. Once again, that's the reason I asked you that you can better try it in using matrix packages rather than doing it straight away. So inverse of a to b. So it's a straight away thing, and if we run this and then print x, we can get the values here. So x basically here is x, y, and z, right? It's a matrix. Ax into b is ax equal to b. So x is the vector, but we have transformed it here we're showing it in a matrix format. If you see this, so X is a matrix with is a matrix with the one column vector. So mathematically X is a vector, and 1 is the value of the first variable, -2 is the value of the second, and the -2 is the value of the third variable. So basically the answer is here. If I have to translate it into X, Y, Z, then I can say that X equal to 1, Y equal to -2, Z equal to -2. This is what it implies. Okay. So we have done it in such a faster way doing this. Now, if you have to use solve function, I don't want to use inverse function if I don't have MATLAB. I just want to use the normal functions that R has. So how to use it? So you can also solve using a function called solve. So if you run this, you get the value, you get the same value. So capital X. So this gives the same value. So what solve does is it takes the matrix of the coefficients of the linear equations, and B is the value on the right hand side. So it basically says it is solving the equations where B is linearly dependent on the columns of A. So that is what it means. Now I can give you a small example. Let us say if we take an example, say 4x equal to 32. Okay, a normal example. This is just a plain example. 4x equal to 32. Then you know that x will be equal to 8, right? So you can try this. You can try 4 and 32, and you get the value of 8 here. So you see the value of 8, or you can say, you can put it in another variable called y, and print it. Print y, you will get it as 8. So basically it means the value 38 is linearly dependent on x, and this one 4, right? So 4 and x. That is the kind of looking at how you derive this using solve. I mean, what is the underlying functionality of solve? That's not very important. I just showed you for an example. So you can see the manual and find out more options in solve. So basically, we have solved this problem without going through any of these flowcharts straight away, because we know that it has a unique solution, and we have found out the examples. Now, if you have to verify, now here you know that A, you know these things, A, value of A. Well, why did I remove it? I'm sorry, I removed it. Okay, let me run this. Okay. Now A is this, B is this, and X is this. So if you see this, the value of A, this is the matrix A, this is the matrix with a single vector column, this is again the third matrix. So AX equal to B, we know. That means if you do a reverse engineering, in that case, AX, we have done the reverse engineering, right? For X, we have done A inverse of B. So now that means if you do a forward calculation of AX into B, AX, then it should be B, right? So if you multiply A with X, it should be B. This is just for our understanding's sake, right? But you will be a little bit surprised with the result here, if I do, let us say, if I run a into x and print the result, what is the answer? What should be the answer? Answer should be 1 minus 2 0. But what is it that we are getting? 1 minus 2 something else. So basically what happens is we have in A, if you see this, I'll just enlarge it. A has an element which is 0.5. So in the decimal, it is represented in a repeating binary. This decimal is of 0.5 is represented in a repeating binary format. So it's a floating point problem, and so it gets rounded in the calculation. This is R is not quite good in this. So what I do is to get the same result as I would round this value. I'll show you how I do. Let us say I put it in a, I do this into x, I put in z, and then what I will do is I will say b fine. Let us say small b, let us not mess with the bigger b. I will say round z digits equal to 0. So this is what I will do to correct it, and when I run B, you get the same answer as the original matrix of minus 1 minus 2 and 0. Correct? So we have proved that Ax is equal to B. Anyway, this is not the idea that, in fact, we don't have to prove it, but I just showed you. Now we'll go back to the first method and solve this instead of solving it using Kramer's rule. We will solve it using the traditional method of adjoint. So in the traditional method, you know that if you remember, x equal to 1 by determinant of A into adjoint of A into B, right? So, and we know the determinant, so let's make it first method. So we go to the first method, and you already know that determinant of A is equal to minus 3. So, and we can straight away find out the adjoint of A, which is something like this matrix, and we can put this value in a variable called, oh no, I have to just remove it. Adjoint of A, okay, and we can multiply it with so we say this is let us say P is equal to adjoint of A and we run it, we get a problem with my mouse actually. Okay, so let me just put it P here. We have P is equal to this and x equal to B by x. This is basically the same first formula, you don't need to worry about. I'm just showing how we can do it. P divided by determinant of A got to keep it. Is a variable. So I'm keeping a determinant of A in a variable det A and adjoint of A in a variable add J, and P in the multiplication of this adjoint A into B, and finally we are doing X will be P is this outcome divided by delta A. So basically it's the same thing which we are doing once again. I'm sorry, I have a problem with my mouse. So should be equal to A. What is the mistake I have done here? I'm trying to clear to B. Let's print B. B is fine. B by data should be fine. Okay. Okay, so we have X here 1 minus 2 minus 2. So this is exactly the same that we derived. If you see the result here, then solve. Now if you do a solve straight away, you get the same answer, right? So 1 minus 2 minus 2. This is the way you solve it using the first method. Anyway, again you can repeat the Kramer's rule as well for this, and you can straight away get the value. So let me show you the Kramer's rule as well for this. So we have this as the, sorry, the mouse is a problem. Okay, we have A as this matrix, and we have B as this matrix. So in Kramer's rule, what we need to find out, we know determinant of A. So if we have already kept the determinant of A in det A, so this is the determinant of A minus 3. So we have to create 3 matrices, substituting the values here in this column first, the value of the columns of B, and then second column as determinant 2 here, and third column in this and the third determinant, substituting the third column, right? So we can use the same method which we used. We say A1, copy of A1 so that we don't mess up with A1, and then we substitute the columns of B in the first column of A and reproduce A1 once again. So if you see, we reproduced A1 with the columns of B 1 minus 2 0, 1 minus 2 0. Now same thing we have to do for A2 as well as A3, A2 as well as A3. Again, just to be sure that here you're substituting column number 2 and here you're substituting column number 3. And this is pretty simple actually. If you see in terms of the answer, you will get answer so fast, and if you do traditionally outside using pen and paper, it will take a little bit of more time, right? Now straight away what we can do is, so we have determinant, we can have determinant of A1, sorry, keep it in a same kind of nomenclature, right? Copy it and we keep it as A2. This one is a variable get A3 for this particular function. We run it. Now we have all the determinants. What is the value of x here? We say small x here. The first variable is, if you remember Kramer's rule, it is determinant of the main, the smaller determinant, the determinant A1 is the main determinant, right? So what is x here? X is 1, fine. Now what is y? Is the determinant A2 by determinant of same this one. So y, if you see the value of y is -2, we are fine. And for third one is determinant of A3 divided by the main determinant, right? So it is 1 -2 -2, and if you use the solve, you get the same value here, just for reconfirmation. So the values are same, 1 -2 -2. So we have proved it even in Kramer's rule. So whichever rule you follow, whichever model you follow, whether you follow the traditional method using adjoint, or you follow the Kramer's rule, or you follow the solve function, whichever method you follow, at the end you can implement it in R. So basically the idea was not to show you the underlying mathematical concepts, but how to implement a solution in R. So that was the idea. And one important thing I thought of covering before I close this, and there are many functions that you can use in MATLAB. You can even, the one which I showed you, some of these manual work you can do in R. But one thing I want to show you, the echelon format is a one in R. So this one you can use, you can see in the echelon format where it has the solution in the last column and the identity matrix here. So even you can to arrive at the identity matrix, you can use some of the functions in MATLAB, which we have not covered in this particular video. There are other functions where you can use to check whether this is a consistent solution or not in MATLAB. I will show you one function where you can use it. All dot equal, this function you can use to check whether you have you can find the documentation of this function actually. Okay. If you run this is so true. So basically it means yes, it's a consistent solution. This is using the rank concepts here. So R is the rank. So you can check these functions in MATLAB. And one interesting thing is, once you have the solution, you can plot your solution and check it graphically what you have done. Now since I have more than 2 variables, so it's a 3-dimensional plot. So you can use this plot equation 3D and by value what was my value 1 minus 2 minus 2, so I can use x limit of c 0 to 4. This is pretty good for me, and I can use a y limit of same thing. So my x and y axis will be from 0 to 4. So this is my limit, and I plot it. Once you plot it, it will plot it beautifully in a graphical format, and this is possible once you have the MATLAB installed. Now you can rotate this as well, and what you can find out is these are the three different planes, the three equations that we had, and those planes will intersect at a point which we have arrived at. So you can do more research on this, and you can rotate this plot to find out that these three lines, the three different planes, the equations that we have intersect in a line that we have found out in our solution. So basically these three planes will meet at these points that we have derived 1 minus 2 minus 2. That is basically the line cutting across, plane clear cutting across. So anyway, the whole idea was to show you different methods to plot a non-homogeneous linear system in R. And thanks for watching this video. Thank you.